Hi everyone, this is Kruti Jai Pancholi, Assistant Professor in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject Analog and Digital Communication System. From this video, you will learn about demodulation of AM. The process of detection is also known as the demodulation. We can also say that it's a reverse process of the modulation. What can we do in this procedure? That we have a block which is known as the demodulator, or you can say that it's a detector. So this is the demodulator block. The input for this demodulator block, it's nothing but the AM wave. It's a amplitude modulated output. So amplitude modulated output that consists of the carrier as well as its shape. Okay, this is like your modulating signal. So modulated wave that consists of this. So it's a AM wave applying to the demodulator. Output of this is the what? It is, I said, the imaginary line, and that's nothing but your information signal. So what you want at the output of this? That we want the original signal back. So demodulation, that is the process in which from the AM wave we can have the output. It's a original input signal or original message signal. Okay, so this way the demodulation, okay, that gives us the original message signal back. There are the various types of the demodulator. Mainly we will discuss about two types of the demodulation. One is the rectifier detector and another one is the envelope detector. Now here it is the diagram of the rectifier detector. This is the of our AM output, amplitude modulated output. So this is the equation of the amplitude modulated wave, and it is passing through the diode. Now this diode D will act as a rectifier. Now the rectifier and this will this output that is given to the filter, and it passes through the capacitor and we can get the output across this R. Now about this, you can see that this is the amplitude modulated wave. That is the input for this rectifier. Now this diode will that will work, okay, that is for the positive half cycle of the modulated wave. So this diode will gives us the output, okay, that is the output of the diode. So it is nothing but only the output of the positive cycle. Fine. Now this positive cycle output that we have, now we want only the information signal. Information signal is the low frequency signal. So what we want to do? We want to eliminate the high frequency component. So we are passing them through the low pass filter. This low pass filter, okay, that removes all high frequency component so that we can recover the envelope of the output. So at the output end we have this. Now at the low pass filter output we have the component that is the AC plus DC. So again we want to remove that component also. So these DC value that we can eliminate it by passing them through the coupling capacitor. So passing them through the coupling capacitor, okay, now we can have the output across this resistor, and that having the 0 DC value. So this is the calculation that we need to perform. So if FM signal is applied to a diode and a rectifier circuit, the negative part of the AM will be removed. The output across the resistor is a half wave rectified version of the signal. The diode acts like a pair of the scissors by cutting off any negative cycle of the modulated sinusoid. Now the rectifier output, the AM signal is multiplied with the XT, that's a pulse train, okay. Hence the half wave rectified output is. Now here you can see the XT, that's a pulse train. In the earlier video we have also seen that, okay, when the pulse train is there, the Fourier series representation of that XT is equal to 1/2 plus 2 by pi cos 2 pi FCT minus 3 by 2 by 3 pi cos 6 pi FCT plus dash dash dash. So now it is VRT across the resistors. This signal is my input signal, modulated output, and this is our pulse train XT. So now this signal multiply with this, okay. So this way you can have this output. Now I will take this inside this. So it is A plus MT cos omega CT by 2 plus the first step if I'll take, it is A plus MT into 2 by pi cos omega CT, it is cos square omega CT. Now this is the higher terms, so that way we will get the all higher terms. Now 1 plus A plus MT cos omega T by 2 plus, if we will take this A plus MT upon pi, what is a 2 cos square omega CT? It is 1 plus cos 2 omega CT. Now again we will take this inside the bracket. So it is 1 plus MT cos omega CT by 2 plus A plus MT by pi plus A plus MT cos 2 omega CT by pi dash dash dash. So here we will take this out. It is my 1 by pi A plus MT plus all other terms that are nothing but all the higher frequency components. So this is the signal and it is the other terms of the higher frequency. So what we will do now, when our VRT is applied to the low pass filter of cutoff frequency, cutoff B hertz, then the output is 1 upon pi A plus MT. So now we are passing them through the low pass filter and it will pass only the low frequency. All high frequency components that are suppressed, okay. So the DC term A by pi, that may also be this A upon, now again if you will open this bracket, it is A upon pi plus MT upon pi, but this A upon pi is what? It's a DC component. So now we know that we put the capacitor, coupling capacitor, which will block this DC, okay, and you will get the desired output, that is the MT by pi. Now using the output can be double by using the full wave rectifier. So this way we can have the rectifier detector output. The second method is envelope detector. Now what is the envelope? That you know that in the AM wave I told you that the imaginary line, which is the envelope of the modulating signal. So second method to get the amplitude modulated output, okay, modulating signal. So that is the envelope detector. It is simple and a highly effective system, and this method is used in most of the commercial AM radio receiver. Envelope detector, okay, that you will see in the figure, fine, and it is used for the m less than 1, while the modulation index that is less than 1, this envelope detector we can use, but while the m greater than 1 is there, this envelope modulator won't produce the output for, so it is a limitation that it will not work for the m greater than 1. Okay, so now we will see the diagram. This is the diagram of the envelope detector. Very simple things are there. It is your AM wave, fine. To protect this diode, there is a one resistance is attached in series with this. So your name is RS. Now there is a capacitor, okay, and there is a output resistance, okay, that is connected in this, fine. So this RL resistance which is connected over here. So now to understand about the envelope detector, very first we should be clear about the elements which we have connected in the diagram. So it is the diode. Now we can assume that it is a simple ideal diode. Now this is the ideal diode, and I can say that, okay, this is nothing but the P, and it is what? This is the N. It's a PN junction diode. So when the P is greater than N, when the P is greater than N, okay, you know that the diode that becomes the forward bias, and when it forward bias, okay, it can be the short circuited. But when the P less than N, when this potential, okay, this P less than N, it is reverse bias and it works as a open circuited. Similarly over here, that there is a capacitor that we have connected, it's a RL. When this capacitor will charge, so this is the VN in voltage that we are applying, and across the capacitor suppose the voltage is VC. Now this capacitor charges only when the VIN value is greater than VC. VIN value is greater than VC. Then and then capacitor charge. So suppose this is your input signal. This is the zero value of my input voltage. Here you can see that my VIN value increases. So now initially when the VIN value is higher, okay, so what happened? That capacitor that charges, and at that time the diode that is the forward bias. Now the capacitor discharges. When the capacitor discharges, only when the VIN value is less. Now here you can see that VIN value is higher, from this point the VIN value is decreases. So VIN value that is less, and you know that the capacitor already charged. So this voltage across this capacitor that is again more. So VIN value when less than VC, the capacitor discharges and the diode is reverse bias. So when the capacitor charges, at that time the charging constant is Rs multiplied by C, and when it discharges, the discharging constant is RL into C. So these are the concepts that is required to understand the functioning of envelope detector. So now here again I put the diagram on both the side, that it is the RS, purpose of this to protect the diode. It is the load resistance. It is the AM wave. So you can see over here, this is the AM wave. Now what we said, that when the VIN is greater than VC, V in value, here the V in value that is increases, and capacitor initially not charged. So V in value greater than Vc, capacitor that starts charging. Fine. Now what happened? That the capacitor discharging, okay, because here you can see that this is falling, so capacitor discharging, again capacitor charge, capacitor discharge. When it charges, it depends on to which value? Charging constant RSC. This charging constant and discharging constant through which we can get. So if the RC value is too large, okay, we can see over here the envelope. So it will detect the envelope using this. So we can have the envelope detector output, that is this. So you can see that it is nothing but my modulating signal. So during the positive half cycle of the input signal, diode is forward bias. Diode forward bias, then capacitor charge. It charge up to the peak value of the input signal. Now when input signal falls, what I said? Input signal falls. When input signal that falls below this value, the diode becomes reverse bias. And when the diode reverse bias, capacitor discharging through the load resistance RL. So discharging process continues until the next positive half cycle. So when the input signal becomes greater than the voltage across capacitor, I said V in greater than Vc, diode again conduct. So this procedure that repeats, okay, so then and we can detect the whole envelope. So the charging time constant is Rf plus Rs into C. Now as I said that it must be short compared with the carrier period. Okay, so the capacitor charges rapidly and thereby follows the applied voltage up to the positive peak when the diode is conducting. So the condition for the envelope detector is, first is the M less than 1. Modulation index is less than 1. Second is this time constant, that value that is much more less than the 1 upon the Fc. Okay, and on the other hand, the discharging time constant must be long to ensure that the capacitor discharging thoroughly through the load resistor RL between the positive peak of the carrier wave, but not so long that the capacitor voltage will not discharge at the maximum rate of the change of the modulating wave. So this way the discharging time constant shall satisfy this condition, that the 1 by Fc much more less than the RLC less than or equal to 1 by W, and it is the bandwidth of the message signal, and this results is that the capacitor voltage or the detector output is nearly the same as envelope of the modulate AM wave. So it is about the envelope detector. Now we will learn about the advantages of AM. So advantages of AM in that it is very easily generate, okay, as well as the demodulation. So modulation, demodulation process that are very easy. It's a cost effective, that you have seen that only simply we have used the diode for demodulation. Also we have seen the AM modulation method. Again in that we are using the transistor and simple component, okay, for generating this. So AM systems are cost effective and easy to build. Disadvantage: AM contains unwanted carrier component, hence it requires the more transmission power. Now here we have seen that, and also we have studied in the equation that the frequency spectrum of the AM wave that consists of the one carrier signal and another one to sideband. So as you have seen that more than one modulating signal, number of sidebands are also increasing. Okay, so when you are transmitting the information by using the AM, so you are transmitting all the components. So now as I said that the sideband contains the same information. So now what happened that we should go for some method by using that we can save the power and we cannot unnecessarily transmit the component. So unwanted carrier component, there is no requirement of the carrier. So we need to go for the method and we have to save the power. The transmission bandwidth is also equal to the twice the message bandwidth. Again we have seen that my FM is 5 megahertz. Then how much bandwidth I need to transmit my AM signal? It is the 2 multiplied by FM. So I require the 10 megahertz. So higher requirement, okay, of the bandwidth and the transmission power, that is more to transmit the AM component. So that is the disadvantage of the AM. Now to solve that all the problems which we discussed in the disadvantage, we should go for the next method, that are the bandwidth efficient amplitude modulations. In that we will study DSBSC, SSBSC and VSB. So it's a double sideband suppressed carrier, single sideband suppressed carrier and vestigial sideband modulation. So in the next lecture we will learn about bandwidth efficient modulation, amplitude modulations. So thank you very much everyone.